which was the real space renormalization group calculation for the 1D Ising model. So we defined a reduced Hamiltonian. So remember, I had a coupling K that's proportional to the inverse temperature, because I absorbed, the beta from the partition function. U to the minus h into the definition of the Hamiltonian coupling or interaction. So what I did was a real space decimation of the one-dimensional chain with a scale factor of b equals 3, which means that for every 3 sites, if these are sigma variables, I decimated this so that the degree of freedom at the next RG step, sigma prime, just consists of 1 variable, or 1 degree of freedom. So this led us to the recursion relation, which I defined as K prime. It's 1 step of the renormalization group procedure. It's basically applying this complicated nonlinear transformation to K. Okay. And that recursion relation is the thing that we'll study now. It was inverse hyperbolic tangent tan h cubed K. And I defined x as hyperbolic tan h, right? So then I have x prime equals x cubed. So that part. So we'll turn back to this in a minute. So that partition function, remember, is invariant. It doesn't. The z doesn't change through this exact RG transformation, except in form. What you've done is you've traced out. Remember, we decimated, so we traced out 2 degrees of freedom for every block. And so that left us with z, which is z of k. Let me write it like that. So that's what I have written up here. This is now the trace over the renormalized, or the coarse-grained, if you will, degrees of freedom. E to the minus h prime, written in terms of those degrees of freedom, which again is zk prime. And that h prime is sort of what we were chasing in some sense. I mean, the RG recursion relation's physically important for the RG, but it's also important that the form of h doesn't change after a rescaling step. So in terms of, we call these sigma big I's here, just to keep them straight. So I have small, lowercase, the original UV, if you will, length scale, and uppercase for the next RG step, and over 3 log, 3 kappa, gosh, 3 kappa. And I call this thing N G of K. So it depends on the couplings, but it doesn't depend on, the variables or the degrees of freedom that are contained in the trace. And as you can see from this first part of the Hamiltonian, you know, the H prime has, besides this, call it a constant. The first part of the Hamiltonian only depends on nearest neighbor variables in this coarse-grained picture, right? So if this is I plus 1 here. So the interaction's gone from nearest neighbor at the first RG level to nearest neighbor after one step of coarse graining. So that's called self-similarity. Self-similar. Then I can write that, I can also write that partition function by pulling out, right, this ngk. And you'll see why it doesn't matter, is because it turns into a prefactor in front of z. So you take derivatives and so on, ratios of partition functions in free energies. These short wavelength degrees of freedom, or these, you know, these parts that come from the lattice transformations don't matter. So you can imagine pulling that out and redoing this again and again. So we've done, you know, k to k prime. We could do k prime to k double prime, and k double prime to k triple prime, and so on. And if we did that, let me just say one more thing before I do that. No, that's fine. So the additional term doesn't affect expectation values. That's what I wanted to write. Okay, so the main content, so I want to reiterate this process many times. So the content of the RG equations lies in that x prime equals x cubed. And that's what we'll examine when we iterate this process. If people say RG equation, that's usually what they mean. So imagine iterating this, you get k double prime, k triple prime, and so on. If R is that functional dependence, which in most cases it won't be as simple to solve as it was in this 1D case. And if k prime is equal to r of k, I guess you don't want to use a bunch of primes. You could call it k1. Then k2 is the same transformation, r, but you apply it to, k prime. So k1, say. And you keep going. And the idea is that you're doing that a large number of times, over and over again. Let me draw it right here. So in this case, you can visualize this iterative process. And what you're doing is you're updating, again, x prime is x cubed over and over again, right? So one way to visualize this is to plot, x cubed, some curve. These are hyperbolic tangent functions. Okay, so x is defined, so x is tan h, it's defined between 0 and 1, right? So we can look between 0 and 1. And what the RG procedure is two steps, remember. It's coarse graining and then rescaling. So coarse graining means doing this procedure. So visually you can imagine, see if I can get this right. Well, those are supposed to intersect. That's just a straight line, x equals, call it x prime. So I can imagine starting at some arbitrary value of coupling, right, k, because that's it's like temperature. So imagine that J is fixed, and I start at some temperature. And then I define x. My coarse graining step is calculating x cubed. Okay, so this is x. It's the first step of my RG. And then I calculate x cubed. And then the rescaling is like taking this x cubed and making it the x of the next step, right? In this step here. So you can visualize that by rescaling over to the x cubed goes to x line again. And this would be my x, say 1. 1 RG step. Coarse grain again. Rescale. And that would be my x2. Coarse grain again. Rescale. Coarse grain again. Rescale. So that's just a way of visualizing that iterative process. It's different for every different system you study. Depends on the form of this RG equation. And so what's going on here is you're flowing towards x equals 0, right? And so what are those limits? So remember, k is j over t. So if x goes to 0, then what we're doing is we're flowing towards high temperature. If I approach the other way, x goes to 1 from below, then this would be low temperature. So there's only two ways that this iteration can go. If you start at any sort of arbitrary x greater than 0, so remember that's like saying starting at some temperature, but less than t equals 0. So if x equals 1, t equals 0. So even if you start arbitrarily close up here, and you start iterating, so x equals x, x prime equals x cubed, rescale, coarse grain rescale, coarse grain rescale. Doesn't matter how close you are to x equals 1, you'll always flow to x equals 0 by this iterative process. So that's the essence of the renormalization group. It's understanding how, when you take these number of iterations to infinity, how your temperature flows, if you will, right? That's called renormalization, that flow. So a way of understanding that physically is that for any temperature that isn't T equals 0 exactly, you're in the same phase as the phase described by this point here. Okay. So that's the interpretation of what the RG is telling you. So there's two fixed points. One of the fixed points, the fixed points again are defined when the iteration stops working, right? So those are the two fixed points, the stationary points on that diagram, if you will. Defined by something like K star equals R K star. I think that's how I define them. So they're at 0 temperature and infinite temperature, but their behaviors are different. So any perturbations in temperature will make you always flow to the x equals 0 fixed point. So the x equals 1 fixed point is called unstable. It's unstable just like you have unstable equilibrium, right? Any physical perturbation will make you flow to the other fixed point. So the RG flow diagram which there's only one coupling, K. So we just draw a one-dimensional RG flow diagram. Okay, so I have X's, so let me go back to K's. So I have two fixed points, K equals infinity and K equals 0, which correspond to T equals 0. So I've ordered them so that temperature is 0 on your left as usual, and T equals infinity. And you have an unstable and a stable fixed point. Okay, so this stable fixed point is the one that you flow to. It's attractive, so it's up here. Stable fixed point. And then this one is the unstable fixed point. And you represent the instability by arrows on this diagram. So if you're at the unstable fixed point and there's any perturbation in temperature, that's the flow of the RG fixed point, then you flow into the infinite temperature fixed point. So this is the sort of high or long wavelength, description. And that's what the RG is doing, is basically successively eliminating like these G of Ks in some sense. So it's successively somehow ignoring the shorter and shorter, wavelength, or shorter and shorter distance degree of freedom as you go to every different RG scale. And so this simple RG flow diagram is like the essence of what the RG is. It tells you a lot right away. It tells you that there's no, there's no stable, say, ferromagnetic phase in one-dimensional models or something like that, right? So if you did the RG for a Potts model or any other RG model, any other Ising discrete symmetry model, in one dimension, you would always find the same flow diagram. What you're going to do on your assignment is you're going to add another coupling to this, like another axis for the magnetic field. And you'll see that there's more fixed points in that case. But in absence of that magnetic field, you always have this RG flow diagram, irrespective of the specific sort of Hamiltonian you start with, or the specific way that you do that decimation. On your assignment, I'll have you do B equals 2. Okay, so we did 3. Doesn't matter. You'll get a different RG flow equation, but you'll get the same RG flow diagram. And again, it tells you there's a stable phase, which is like the paramagnet. Okay, so this is the paramagnet phase. Oops. And this is the ferromagnetic phase. And so this confirms what you know physically from, say, Peierls argument or something like that, that you don't have a stable phase, a ferromagnetic phase in a 1D model for any finite temperature. Any finite temperature, any perturbation off T equals 0 makes you flow up into this stable fixed point, which is just the representation of the phase. Okay? So let me just write that. So the long distance, I guess, degrees of freedom. It's like when I showed you those movies. That was that's higher dimension, so let's talk about that. But in those movies, if I was moved right off of the critical temperature, then as I zoomed out, so as I went to higher and higher or longer and longer distances, at some point I decided what phase I was in, right? And if you remember that movie, there was actually 3 fixed points. There's one at low temperature, one at high temperature, one in the middle. And if I was moved off of that fixed point a little bit, either way, then I would flow as I zoomed out to something that looked like either the high temperature or the low temperature phase. So the difference between this and what you saw in that movie was this is a one-dimensional model. And so in one dimensions, you get this type of flow. So what about higher dimensions? So how can we understand that RG flow that we saw in those movies? So let's imagine doing the same procedure, but instead of a 1D Hamiltonian, let's think of a 2D Hamiltonian. And I could try it, but let me just tell you what happens. It doesn't work. So these block decimation pictures in real space, there's a reason why they don't work in higher dimensions. So let's not do a procedure like a full RG like we did for this, but let's just make some general observations. We'll do an analytical RG procedure in general dimensions and momentum space, which is more powerful analytically than these real space pictures. So remember in 1D, here when I had K prime equals, inverse, hyperbolic, whatever. Let's just explore the limits of that. I'll just write it again here. So. Something like that. If I took the limit, so I want the limit of K, say K prime, going to infinity, so down at 0 temperature. That limit is also the same limit if I took it just in the original variable K. So near that fixed point, it's like physically, I don't care whether or not I'm in the original or the rescaled variables. It's like saying, it's like saying near this fixed point, my Hamiltonian is self-similar. That's what I found over there. It doesn't really matter. It's always a nearest neighbor Hamiltonian. And the coupling, so very roughly, the couplings are similar. They're not scaling somehow with a dimension. So near that limit, I'm going down to 0 temperature. I'm basically in a ferromagnetic state. Right? If I look at an individual length scale. And so before the RG transformations, I have some defects, as you know, down here. It's described by a paramagnet. But generally, if I look at an individual block, I can assume that interactions are strong enough compared to temperature that things generally point in the same direction. And so in that limit, and note that the interactions are mediated by boundary spins. So if I look at that picture up there, the interactions are between sigma I, 1, 2, say 3 and 4 on the top line, or sigma I, big I, and I plus 1. So in both cases, so I have blocks here. Sigma 1, sigma 1. Sigma 2 was sigma 1 prime, I don't know. Sigma 3, sigma 4, sigma 5. Sigma 5 was sigma 2 prime in that block decimation procedure. So K prime was somehow, right? So K prime was the interaction between 3 and 4. But now I'm taking the trace over 3 and 4, but 3 and 4 are essentially, because of the temperature, in a high probability, they're in state 1. So it's like K, sigma 3, say expectation value, sigma, what did I say, sigma 4 expectation value, something like that, right? And these are fixed, these are evaluated, but essentially fixed to be 1 in that limit. So you can imagine this is essentially unchanging, right? It's basically saying, as you approach that fixed point, this recursion relationship doesn't change much. But in 2D, things are different. Let me imagine doing the same block decimation. Where I now have 3 by 3 blocks. So I would still say my scaling factor is B equals 3. But my interactions, if K is the blue, then K prime is more like 3 times the blue, right? This is just a very simple argument, but so more generally, K prime would be B is 3. So B to the D minus 1. That's what this boundary is 1 dimension lower than the system. So I'd say B to the D minus 1 K. So generally, only when it's 1 dimension, this thing becomes independent of D, right? So K prime, we expect K prime to be greater than K by this argument. But remember, K is like inverse temperature, right? So we're always increasing K, right? So it's like we're always decreasing the temperature as we do this transformation in higher dimensions. So it means that if we perturb ourselves away from that T equals 0 fixed point, the RG flow will push us back. So T equals 0 fixed point should be locally stable. So it appears physically different than the one-dimensional case. In 1D, we've already shown that it's locally unstable. But just like the 1D case, there's no reason that the paramagnetic state isn't stable. Like physically, if you're at infinite temperature and you slightly lower your temperature, you have to still be in the paramagnetic phase. So that one always has to be stable. So in higher dimensions, just from this simple argument, in the limit when temperature goes to 0, you expect there to be 2 stable fixed points. say stable paramagnetic phase. So another stable fixed point. So even though we still have one variable, k, then the diagram should look like the diagram we expected in 2D. Where we have a low temperature, an intermediate temperature, and a high temperature fixed point. Okay, so this is k equals infinity. It's t equals 0. This is k equals 0, t equals infinity. And the intermediate one is just some k star equals k, or t equals t star. So this one's stable. Any perturbations push me back. This one's stable. Any perturbations push me back. So the RG flow has to look like this. So that intermediate fixed point, which you know already in 2D is like the Onsager fixed point. That in 2D that would be TC 2.269 for Ising. So that phase transition is unstable. That's what you saw in those videos. I should have played them again. But remember when you were 0.997 away from TC, and then you rescaled, you went to longer and longer wavelengths, you flowed down into one of the zero temperature states, either all up or all down. And if you're 1.003 TC and you zoomed out to some massive length scale, you flowed up to this fixed point. So the phase transition in the 2D Ising model, in the 3D Ising model, and the 4D Ising model correspond to some unstable fixed point. And we're going to study this a lot more in the class. That's called the Wilson-Fisher fixed point. So these two, it turns out, will be described by Gaussian theories. We can do the integrals exactly in momentum space. But this one, we need some sort of approximation. It corresponds to a 5-4 theory. You have to include interactions to get that fixed point. And so those interactions, we're going to start this maybe Friday, the framework for this momentum space RG. They'll be handled with a type of, I guess, approximation method called an epsilon expansion. Okay, but we still have some more general scaling arguments that we can sort of glean out of this RG framework before we start into this explicit calculation. Any questions about that? Does that make sense? Just some vague argument, but it gives us what I think we expect in 2D and higher. Okay, so let me just talk generally about, let's keep this idea that we're just looking at general properties of real space RG in higher dimensions. Okay, I have my fixed point equation here. So the functional dependence of the RG is that R And we also know this is something I already told you, but it's worth thinking about again. Under that transformation R, the length scales are reduced by a factor of B, right? B is your scale factor. So the correlation length prime, I might have called it, which is the correlation length in terms of K prime, is 1 over B, the correlation length K, which is just what I was calling the correlation length. So it means at the fixed point, you know, I still have this relationship. I still have this rescaling of length scales, but then the correlation length at K star, which I'll say is like K prime, so it's, you know, it's after one step of the RG. The K and K star haven't changed. They haven't scaled anymore. It's like you've flowed into one of these fixed points, right? Nothing's changing anymore. It's like you've gone down to that stable fixed point at x equals 0. And as you're in that limit, nothing's moving anymore. So how can something be equal to something times a scale factor? Correlation length is just a number, right? So you have a pardon? This is final psi. Oh yeah, so psi, or what the hell is this thing called? Z, psi, whatever. This is 1D. But sorry, what are you asking? So, or what are you saying?
I want to know the final step.
Here? Yep. I'm just rescaling the length scale. There's just a length scale that whatever it is, L prime goes to 1 over B L. L double prime goes 1 over B L prime. So what I'm trying to get at here is this only works if that correlation length is 0 or infinity. Infinity is what we've been talking about in terms of a diverging correlation length. But you could also have it could also be true that correlation length is 0.
The confusing thing is psi over K and psi. So,
oh, you mean this thing here? Oh, sorry. This thing you're talking about. Yeah. I'm just defining this and this to be the same. This is just notation. I think previously I called it prime, but I just want you to think of the fact that if I'm at a fixed point, okay, so I could write this like this. Chi star is 1 over B. So what is the correlation length at the fixed point? That's all I'm saying. I just forgot that 1 over B there. I think that's what you're getting.
That equation looks confusing. So psi over K star equals 1 over B. Psi over K star. Does this make sense?
Would it work better if the equal signs were replaced with arrows? Because it's really flat, isn't it?
Yeah.
Or we have to put star onto the psi itself.
Right. So the point is, the star comes after an RG transformation. So it's like you're at the fixed point, you're performing the map, right? The thing's not moving. The thing's not changing. I don't know. Don't read too much into this. All I'm saying is that intuitively, this can only be true if you've flown to a state where this thing is 0 or this thing is infinity. And we've already been thinking about this case. Somehow the point with the RG is that, you know, the length scale, the only characteristic length scale in this system has diverged. And so it's no longer, there's no longer any length scales. But you see that you can also get trivial cases where the correlation length is 0, and that's what's going on up here. There's no correlation length up here, even though this is a fixed point. So I'm just saying that sometimes these are trivial, and sometimes these are non-trivial. So we'll find that the Wilson-Fisher fixed point, the thing we're going to chase down in momentum space, is non-trivial. It's a non-trivial fixed point, unlike, say, the high temperature fixed point. So at high temperature, you're just in a paramagnetic state, and you know, at some finite but not infinite temperature, you can imagine nearest neighbors still being slightly correlated. You know, maybe here. There's still some correlation, but at infinite temperature, really there's no more correlation at all. You know, all bonds are broken in the system, right? So that corresponds to this trivial case. Let me talk about if you're near the fixed point, then you could do a Taylor expansion of the functional dependence up there. You never know that R. You're gonna, I mean, maybe you know it in some, you know, maybe it's in some closed form, but it might not be some simple linear equation. So the strategy we're going to take when we do these types of analyses is to linearize the RG equations. So to do that, you have to make an approximation. You're usually making the approximation that you're very near the fixed point. Okay, so you've flowed very close to one of these fixed points. So let's look at K prime. Doesn't matter which fixed point, whichever one you're studying. So that functional RG dependence. And we're imagining we're not exactly at the fixed point, but we're just so close that K minus K star is small. So then we can approximate K prime with sort of K evaluated at K star plus the derivative at K star, K minus K star. Okay, so just a Taylor expansion. We have R, we have its derivative, functional derivative. We could have higher order terms if we wanted to. We're going to eventually just be dealing with sort of this piece here, which is basically the linearized equation. I'm going to define basically the scaling dimension y through this equation. So that r, the derivative of r, can always be related to y through the scale factor b, like this, okay? And, oh, I should have wrote this here, but you're near the fixed point, you're just k star. So this defines so this is the function evaluated, right? And then here I'm multiplying by k minus k star. Okay, so that gives us a definition of y, which is pretty much useless, but at least it tells you what it is. And y is going to be sort of the central object that we're chasing down in these RG equations. Because that's going to tell us how our flows look in these RG flow diagrams. Y is going to tell us whether or not we're stable or unstable with respect to the variables. Here we only have one, k, right? But how do you know if, there's a general argument here, but how do you know from the RG equation, the recursion relation, whether or not you have stable or unstable flows? So y is going to tell us that. So y is related to that derivative. Also probably we'll use this again because I have k star here now. So k prime minus k star is just b to the y. This is probably the one that we'll use. So it's like a small distance away from the fixed point, is related to the distance at the next lower length scale by b to the y. It's like the scaling dimension of that transformation in the coupling. That's what y is. Okay, so remember the correlation length? I'll say it's the reduced temperature to the minus nu, the scaling exponent. So the reduced temperature is just T minus Tc. Let me see if this works. I have k minus k star. That's 1 over T minus 1 over Tc. Yeah. So very near to the critical temperature is some constant, Tc minus T. Okay, so maybe the signs change. So I can also say that this thing, I'll just say is k minus k star. Why not? And since B is related to the correlation length, I'll say so 1 over B, which way do I want to do this? I can use this equation to relate nu to y here. So k minus k star to the minus nu. Right. Oh yeah, I just wrote it here. So let me put b on this side here. Okay, so that's just rewriting the correlation length. But the right-hand side here, so it's 1 over b. So now I can use that equation. So it's actually b, so b times b to the y, k minus k star. Everything in square brackets to the minus nu, right? That's just relating here to here. Okay, so if I bring b inside, b minus 1 over nu, by, k minus k star. Everything is minus nu. Okay, so I have left-hand side and right-hand side. So that gives us me a constraint on b to these powers. They basically have to be 1. Or no, y minus, is it 1 over nu is equal to 0, right? What? So you just related a critical exponent to basically the scaling dimension. And the scaling dimension is defined through that derivative here. So the critical exponents are related to the derivatives of the RG transformation. So this was kind of the thing that we were chasing all along. It's like, if you want to calculate critical exponents, you don't have to do this iteration to infinity. You just have to do one step of the iteration. You do it very near to the fixed point. You're very near to either this fixed point or this fixed point or whatever. And if you know how to take the derivative, then you know what y is. And here we've just found a way to relate y to the exponent of the correlation length. And so it turns out that you can relate, for different parameters, say field and temperature, you can relate the different scaling dimensions to all the different exponents. And that's how you can calculate exponents using the RG. Oops, I forgot derivatives. So critical exponents are given by the derivatives of the RG transformation at the fixed point, say. Because you evaluate that derivative at the fixed point. So 1 over nu is, this thing here. So you can trace the existence of the fixed points to the assumption that this thing is differentiable, actually. So that you need R to be, you need to have R prime. You need R prime. If you have R prime, you have a critical exponent. differentiability of R at the fixed point. Okay, so I started doing something that was pretty general, and I wasn't talking about the dimension that much here. So why can't I do an explicit calculation of the critical exponents of the 2D Ising model at this non-trivial fixed point with this procedure? So it's all laid out. All I got to do is figure out what that R is. But the point is, it's actually not so simple in 2D. So we've also assumed something important here, and that's self-similarity of the Hamiltonian. I think I'm erasing it now. But we saw that the form of the Hamiltonian, and I emphasize this, in one dimension was just the 1D Ising model again, and that G thing. I didn't seem to care too much about that G thing. I only cared that the form of the Hamiltonian was sigma I plus 1. And what happens in higher dimensions is that self-similarity is violated. So the Hamiltonian starts getting higher and higher couplings. D greater than 1. Next nearest neighbor couplings. So what happens is you actually have, okay, so I got here these blocks. I drew 2 blocks. And I said K, you know, somehow 3 times K prime, you know. Other way, K prime is 3 times of K. But I should have also drawn a block here, and, you know, I would have had a K prime there, but I also would have generated a K double prime here. So I'm not doing it because it's pointless, but if you actually try to do the RG transformation, you would see generation of K double prime in the Hamiltonian in 2D. So the Hamiltonian is no longer self-similar. And as you keep iterating in higher dimensions, you'll actually just generate all interaction parameters consistent with all the symmetries. So you'll get K triple prime, and you'll get, you know, all these different Ks. And at some point, your Hamiltonian becomes long range, and it doesn't make any sense. You can't do this type of analysis anymore because you've generated all those couplings. Okay, so we're not going to do that. You can find that in books, Kadanoff block transformations.
B is greater than 2 or greater than 1?
Greater than 1, sorry. It doesn't work for 2. Okay, so before we start into, I'm just procrastinating on momentum shell RG, but let's just keep talking about scaling theory, because I can still derive a couple things with general scaling theory of the free energy. And I think it's good to build up this intuition for where we're going before we get into the momentum shell, because even though it's precise, you can exactly do calculations at the Wilson-Fisher fixed point. It takes a few classes to get through all the momentum space, basically transformations and stuff. So let's just keep deriving everything we can using scaling functions, which isn't much more. So I want to calculate more critical exponents, not just nu. And I want to do it in the case where there's more than one coupling. So there could be a temperature and a magnetic field. There could be say a K and a K prime in 2 dimensions, like nearest neighbor and next nearest neighbor coupling. There could be all sorts of different things in your microscopic Hamiltonians. And let's look at the free energy first. So let's just set this up and we'll knock it down next class. So I've said this many times, but Z is invariant trace, what did I call this? Sum over sigma e to the minus h, sum over sigma prime. But remember, we have this thing called G. So let me think of the free energy. Remember, I talked about the free energy density last week. The free energy density I'm just going to define as reduced. So the free energy density small f is the reduced free energy per site. Means I don't have any beta out in front. That's all it means. So recall for the 1D Ising, we had a Hamiltonian. Let me write it explicitly. It's sigma prime, which was self-similar prime prime, but had this thing, which I'm not going to write, G of K. That's the self-similarity that doesn't occur in higher dimensions. You don't get this form for the Hamiltonian. So the partition function which I can use I can just invert this equation to get the free energy, is also equal to sigma prime e to the minus h prime sigma prime, which is e to the minus ng, what do I call it, k. And we keep this in the exponential, minus n prime f, I don't know, k prime. So again, that's why you just have an e to the g that's factored out in front. And if we're caring about the non-analytical part of the free energy, or the singular part of the free energy, then we don't care generally about that G of K. But the number of blocks has been reduced. In general D dimensions, it's b to the minus d n, so that f written in terms of these variables k okay, this is something I wrote before, but before we derive the functional forms. So now we know that there's a singular and a non-singular part. So this remains analytic. At the fixed point, whatever that is. And the singularities are contained here. So that singular part transforms, I don't know, call it Fs, and then drop the S. Just simply like that. So close to the fixed point, let's ignore the irrelevant variables. So let's assume we have two variables. I only have one, but I want to generalize this. So this is what I'm going to do on Friday. I want to generalize the fact that we have, just the temperature, but I also want to include anything. But I'm going to call it a field, but it could be Nexter-Saber couplings. It could be whatever. On your assignment, you're going to deal with a field. So we're going to use this form of the singular part of the free energy. Okay, so this is the most important thing. And we're going to derive scaling functions for more than one variable. So each one of these k's is now a set. Okay, and that set can include all sorts of things. But like I say, I'm just going to consider the case where we have a temperature, or an inverse temperature. And these are reduced. Okay, so now I'm going to expand these arguments in this set of couplings. So now I'm going to have different y's. I'm going to have different k's. I'm going to have different y's. I'm going to have y's that just correspond to temperature, and I'm going to have ones that correspond to, say, the field. So I could have T, reduced temperature, say reduced field, for example. So I want to end on time, so I'm not going to go into this now. So what we're going to, because I want to go over the IQC for this journal club thing at 1. So we'll pick this up next time. But what we're going to do is basically just look at the scaling of the free energy when we have more than one variable. So keep in mind, we're going to start from here next time, the free energy. Let's say 2. So it's going to be F set of K B minus D F set of K prime. So from that, I should be able to derive all the exponents, or at least the dependence of all the exponents on the scaling variables. But not just this one example. I'm going to do it for all of them. Alpha, beta, gamma was the susceptibility. So to have the susceptibility, I need to include H, the reduced field. And probably I'll have you do delta on your assignment. So delta was the isotherm, remember, the critical isotherm. And there's also another exponent hidden in the correlation, the 2-point correlation function, which is also related to these y's, okay, these scaling dimensions. So that's what we'll do next class. We'll derive the relationship between all the known exponents, all the ones that we've already talked about, in the case where we have these 2 variables. And then I'm going to derive finite size scaling functions, which we'll use on your computational assignment. And then after I do that, then we'll start into the momentum shell RG. Okay. So if I don't get to the momentum shell Friday, then we'll start doing it on next week on Wednesday. Okay, your assignments are due when I see you next. How are they going? How's that last question? The doable? It's probably the only hard one. Right? I'll have another hard assignment for you Friday. It'll be due in 2 weeks, and then we'll take a break for suicide prevention week, whatever it's called, reading week. Okay. Okay, so see you guys on Friday.